Now let's turn to the analysis of the deterministic selection algorithm that we discussed in the last slide by Blum, Floyd, Pratt, Revest, and Tarjan. In particular, let's prove that it runs in linear time on every possible input. Let's remind you what the algorithm is. So the idea is we just take the rselect algorithm, but instead of choosing a pivot at random, we do quite a bit more work to choose what we hope is going to be a guaranteed pretty good pivot. So again, lines 1 through 3 are the new choose pivot subroutine, and it's essentially implementing a 2-round knockout tournament. So first we do the first round matches. So what does that mean? That means we take A, we think of it as comprising these groups of 5 elements. So the first 5 elements, 1 through 5, then the elements 6 through 10, the elements 11 through 15 in the array, and so on. We sort each of those 5 using, let's say, merge sort, although it doesn't matter much. Then the winner of each of these n over 5 first round matches is the median of those 5. That is the third largest element out of the 5. So we take those n over 5 first round winners, the middle element of each of the 5 in the sorted groups. We copy those over into a new array, capital C, of length n over 5. And then we run the second round of our tournament, at which we elect the median of these n over 5 first round winners as our final pivot, as our final winner. So we do that by recursively calling deselect on C. It has length n over 5. We're looking for the median, so that's the n over 10th order statistic in that array. So we call the pivot P, and then we just proceed exactly like we did in the randomized case. That is, we partition A around the pivot, we get a first part, a second part, and we recurse on the left side or the right side as appropriate, depending on whether the pivot is less than or bigger than the element that we're looking for. So the claim is, believe it or not, that this algorithm runs in linear time. Now, you'd be right to be a little skeptical of that claim. Certainly you should be demanding from me some kind of mathematical argument about this linear time claim. It's not at all clear that that's true. One reason for skepticism is that this is an unusually extravagant algorithm in 2 senses for something that's going to run in linear time. First is its extravagant use of recursion. There are 2 different recursive calls, as discussed in the previous video, and we have not yet seen any algorithm that makes 2 recursive calls and runs in linear time. The best case scenario was always n log n time for our 2 recursive call algorithms like merge sort or quick sort. The second reason is that outside of the recursive calls, it seems like it does kind of a lot of work as well. So to drill down on that point and get a better understanding for how much work this algorithm is doing, the next quiz asks you to focus just on line 1. So when we sort groups of 5 in the input array, how long does that take? So the correct answer to this quiz is the third answer. Maybe you would have guessed that, given that I'm claiming that the whole algorithm takes linear time. You could have guessed that this subroutine wouldn't be worse than linear time. But you should also be wondering, isn't sorting always n log n? So aren't we doing sorting here? Why isn't the n log n thing kicking in? The reason is we're doing something much, much more modest than sorting the length n input array. All we're sorting are these puny little subarrays that have only 5 elements. And that's just not that hard. That can be done in constant time. So let me be a little more precise about it. The claim is that sorting an array with 5 elements takes only some constant number of operations. Let's say 120. Where did this number 120 come from? Well, for example, suppose we use merge sort. If you go back to those very early lectures, we actually counted up the number of operations that merge sort needs to sort an array of length m for some generic m. Here m is 5, so we can just plug 5 into our previous formula that we computed for merge sort. Right? If we plug m equal 5 into this formula, what do we get? We get 6 times 5 times log base 2 of 5 plus 1. Who knows what log base 2 of 5 is? That's some weird number, but it's going to be a most 3, right? So if that's a most 3, 3 plus 1 is 4, multiply that by 5, then again times 6, and boom, you get your 120. So it's constant time to sort just one of these groups of 5. Now, of course, we have to do a bunch of groups of 5, but there's only a linear number of groups, constant per each, so that's going to be linear time overall. So to be really pedantic, we do 120 operations at most per group. There's n over 5 different groups. We multiply those, we get 24n operations to do all the sorting, and that's obviously a big O event. So linear time for step 1. So having warmed up with step 1, let's look now at the whole 7-line algorithm and see what's going on. Now, I hope you haven't forgotten the paradigm that we discussed for analyzing the running time of deterministic divide and conquer algorithms, like this one. So, namely, we're going to develop a recurrence, and remember, a recurrence expresses the running time, the number of operations performed, in two parts. First of all, there's the work done by the recursive calls on smaller subproblems, and secondly, there's the work done locally, not in the recursive calls. So let's just go through these lines one at a time and just do a running tally of how much work is done by this algorithm, both locally and by the recursive calls. So the quiz was about step number 1. We just argued that since it's constant time to sort each group and there's a linear number of groups, we're going to do linear work, theta of n, for step 1. So copying these first round winners over into their special array C is obviously linear time. Now when we get to the third line, we have a recursive call, but it's a quite easy recursive call to understand. It's just recursing on an array that has size 20% as large as the one we started with on n over 5 elements. So this, remember the notation we use for recurrences. Generally we denote by capital T the running time of an algorithm on arrays of a given length. So this is going to be the running time that our algorithm has in the worst case on inputs of length n over 5, because n over 5 is the length of the array that we're passing to this recursive call. Good. Step 4, partition. Well, we had videos about how to implement partition and why it's linear time. We knew that all the way back in quicksort. So that's definitely theta of n. Step 5 is constant time. I'm not going to worry about it. And finally, we get to lines 6 and 7. So at most, one of these will execute. So in either case, there's one recursive call. So that's fine. We know in recurrences, when there's a recursive call, we just write capital T of whatever the input length is. So we just have to figure out what the input length here is. It was n over 5 in line 3. So we just have to figure out what it is in line 6 or 7. Oh yeah, now we're remembering why we didn't use recurrences when we discussed randomized quicksort and the randomized selection algorithm. It's because we don't actually know how big the recursive call is, how big the input passed to this recursive call in line 6 or 7 is. Line 3, no problem. It's guaranteed to be 20% of the input array because that's how we define it. But for line 6 or 7, the size of the input array that gets passed to the recursive call depends on how good the pivot is. It depends on the splitting of the array A into the two parts, which depends on the choice of the pivot P. So at the moment, all we can write is T of question mark. We don't know. We don't know how much work gets done in that recursion because we don't know what the input size is. Let me summarize the results of this discussion. So I'm going to write down a recurrence for the deselect algorithm. So let T of n denote the maximum number of operations that deselect ever requires to terminate on an array input of length n. This is just the usual definition of T of n we use in recurrences. What we established in our tally on the last slide is that deselect does linear stuff outside the recursive calls. It does the sorting of groups of 5, it does the copying, and it does the partitioning. Each of those is linear, so all of them together is also linear. And then it does two recursive calls. One whose size we understand, one whose size we don't understand. So for once, I'm not going to be sloppy, and I'm going to write out an explicit constant about the work done outside the recursive calls. I'm not going to write big O of n. I'm going to actually write C times n for some constant C. So of course, no one ever cares about base cases, but for completeness, let me write it down anyways. When deselect gets an input of only one element, it returns it. Let's call that one operation for simplicity. And then in the general case, and this is what's interesting, when you're not in the base case, when you have to recurse, what happens? Well, you do linear work outside of the recursive calls, so that's C times n for some constant C. C is just the linear, the expressed constant in all of our big thetas on the previous slide. Plus the recursive call in line 3, and we know that happens on an array of size n over 5. As usual, I'm not going to worry about rounding up or rounding down, it doesn't matter. Plus our mystery recursive call on an array of unknown size. So that's where we stand, and we seem stuck because of this pesky question mark. So let's prove a lemma, which is going to replace this question mark with something we can reason with an actual number that we can then analyze. So the upshot of this key lemma is that all of our hard work in our choose pivot subroutine in lines 1 through 3 bears fruit in the sense that we're guaranteed to have a pretty good pivot. It may not be the median, it may not give us a 50-50 split. then we could replace the question mark with 1/2 times n, but it's going to let us replace the question mark by a 7/10 times n. Now, I don't want to lie to you. I'm going to be honest, it's not quite 7/10 n. It's more like 7/10 n minus 5. There's a little bit of additive error. So taking care of the additive error adds nothing to your conceptual understanding of this algorithm or why it works. For those of you who want a truly rigorous proof, there are some posted lecture notes which go through all the gory details. But in lecture, I'm just going to tell you what's sort of morally true and ignore the fact that we're going to be off by 3 here and 4 there. And it will be clear when I show you the proof of this lemma where I'm being a little bit sloppy and why it really shouldn't matter, and it doesn't. So to explain why this key lemma is true, why we get a 30-70 split or better guaranteed, let me set up a little notation. I'm getting sick of writing n over 5 over and over again, so let's just give that a synonym. Let's say k. So this is the number of different sort of first round matches that we have, the number of groups. I also want some notation to talk about the first round winners, that is the medians of these groups of 5, the k first round winners. So we're going to call xi the ith smallest of those who win their first round match, who make it to the second round. So just to make sure the notation is clear, we can express the pivot element in terms of these x's. Remember, the pivot is the final winner. It wins not only its first round tournament, but also the second round tournament. It's not only the middle element of the first group of 5, it's actually the median of the n over 5 middle elements. It's the median of the medians. That is, of the k middle elements, it's the k over 2th order statistic, k over 2th smallest. I'm saying this assuming that k is even. If k was odd, it would be some slightly different formula, as you know. So let's remember what we're trying to prove. We're trying to prove that for our proposed pivot, which is exactly this element x sub k over 2, it's exactly the winner of this 2-round knockout tournament, we're trying to argue that for this proposed pivot, we definitely get a 30-70 split or better. So what that means is there better be at least 30% of the elements that are bigger than the pivot. That way, if we recurse on the left side in the first part, we don't have to deal with more than 70% of the original elements. Similarly, there better be at least 30% of the elements that are smaller than the pivot. That way, if we recurse on the right-hand side, we know we don't have to deal with more than 70% of the original input elements. So if we achieve this goal, we prove that there's at least 30% on each side of xk over 2, then we're done. That proves the key lemma that we get a 30-70 split or better. So I'm going to show you why this goal is true. I'm going to introduce a thought experiment, and I'm going to lay out it abstractly. Then we'll sort of do an example to make it more clear, and then we'll go back to the general discussion and finish the proof. So what we're going to do is a thought experiment for the purposes of counting how many elements of the input array are bigger than our pivot choice and how many are smaller. So in our minds, we're going to imagine that we take the n elements in A and we arrange them in a 2D grid. So here are the semantics of this grid. Each column will have exactly 5 elements, and it will correspond to one of the groups of 5. So we'll have n over 5 columns corresponding to our n over 5 groups in our first round of our tournament. If n is not a multiple of 5, then one of these groups has size between 1 and 4, but I'm just not going to worry about it. That's some of the additive loss, which I'm ignoring. Moreover, we're going to arrange each column in a certain way so that going from bottom to top, the entries of that group go from smallest to largest. So this means that in this grid we have 5 rows, and the middle row, the third row, corresponds exactly to the middle elements, to the winners of the first round matches. So because these middle elements, these first round winners, are treated specially, I'm going to denote them with big squares. The other 4 elements of the group, 2 of which are smaller, 2 of which are bigger, are just going to be little circles. Furthermore, in this thought experiment, in our mind, we're going to arrange the columns from left to right in order of increasing value of the middle element. Now remember, I introduced this notation, x sub I is the ith smallest amongst the middle elements. So a different way of what I'm trying to say is that the leftmost column is the group that has x1 as its middle element. So among the n over 5 middle elements, one of the groups has the smallest middle element. We put that all the way on the left. So this is going to be x1 in the first column, the smallest of the first round winners. x2 is the second smallest of the first round winners. x3 is the third smallest, and so on. At some point we get to the median of the first round winners, xk over 2, and then way at the right is the largest of the first round winners. And I'm sure that you remember that the median of medians, which is xk over 2, is exactly our pivot. So this is our lucky winner. I know this is a lot to absorb, so I'm going to go ahead and go through an example. If what I've said so far makes perfect sense, you should feel free to skip the following example. But if there's still some details you're wondering about, I'm hoping this example will make everything crystal clear. So let's suppose we have an input array. I need a slightly big one to make the grid make sense. So let's say there's an input array of 20 elements. So there's going to be the input array, which is in a totally arbitrary order. There's going to be the version of the array after we sort each group of 5. And then I'm going to show you the grid. So here's the input array we're going to use. Let's now go ahead and delineate the various groups of 5. So after sorting each group, we get the following. From each group, there's a single winner, namely the middle element. So that would be the 12 and the 6 and the 9 and the 14. Those are the 4 survivors from the first round of the tournament. And the median of these 4 elements, which at the end of the day is going to be our pivot, is the second smallest of the 4. That's how we define the median for an even number of elements. So that's going to be the 9. So this first transformation from the input array to this vaguely mini-sorted version of this input array with the groups of 5 sorted, this we actually do in the code. This happens in the algorithm. Now this grid we're just doing in our minds. Okay? We're just in the middle of proving why the algorithm is fast, why the pivot's guaranteed to give us close to a 30-70 split or better. So let me show you an example of this grid in our mind, what it looks like for this particular input. So the grid always has 5 rows. The columns always have 5 elements because the columns correspond to the groups. Here, because n equals 20, n over 5 is 4. So there's going to be 4 columns and 5 rows. And moreover, we arrange the columns from left to right so that these middle elements go from smallest to largest. So our middle elements are 6, 9, 12, and 14, and we're going to draw the columns in that order from left to right. So first we'll write down the middle elements, the middle row, from decreasing to increasing, 6, 9, 12, 14. Again, the median of these is our pivot, which is the 9. And then each column is just the other 4 elements that goes along with this middle element from decreasing to increasing as we go from bottom to top. So this is the grid that we've been talking about on the other slide in this particular example. So I hope that makes what we're talking about clear, what these X's mean and what order we have amongst the rows, amongst the columns, and so on. So let's go back to the general argument. Here is the key point. Here is why we're doing this entire thought experiment. It's going to let us prove our key lemma that we get a 30-70 split or better. 30% of the stuff at least is less than the pivot. 30% of the stuff at least is bigger than the pivot. So why is there at least 30% of the stuff below the pivot? Why is the pivot bigger than at least 30%? Well, it's bigger than everything to the left and everything below the stuff to the left. That is, we know that xk over 2 is bigger than the k over 2 minus 1 elements that are to the left of it, those other middle elements that it's bigger than. That's because it's the median of the medians. So if we just go straight west from the pivot, we only see stuff which is less. Furthermore, these columns are arranged from decreasing to increasing order as we go from south to north, from bottom to top. So if we travel south from any of these smaller x sub i's, we only see stuff which is still smaller. So all we're using here is transitivity of the less than relation. You go straight west, you see stuff which is only smaller. From any of those points, if you go southward, you'll see stuff which is even smaller than that. So this entire yellow region, everything southwest of the pivot elements is smaller than it. And that's a good chunk of the grid, right? So for all of these columns, it's basically 3 out of the 5, or 60% of them, are smaller than the pivot, and half of the columns essentially are in this part of the grid. So if the pivot's bigger than 60% of the stuff in 50% of the groups, that means it's bigger than 30% of the elements overall. And if we reason in an exactly symmetric way, we find that the pivot is also smaller than at least 30% of the array. So to find things bigger than the pivot, what do? First, we travel eastward. That gives us middle elements that are only bigger than it. And then we stop wherever we want on our eastward journey and we head north. And we're going to see stuff which is still bigger. So this entire northeastern corner is bigger than the pivot element. And again, that's 50%. That's at 60% of roughly 50% of the groups. Returning to our example, the southwest region of the 9 is this stuff, 1, 3, 4, 5, 6. Certainly all of that is smaller than the 9. You'll notice there's other things smaller than the 9 as well. There's the 8, there's the 2, there's the 7, which we're not counting. But it depends on the exact array, whether or not in those positions you're going to have stuff smaller than the pivot or not. So it's this yellow region we're guaranteed to be smaller than the pivot. Similarly, everything northeast of the pivot is bigger than it. Those are all double-digit numbers, and our pivot is 9. Again, there's some other stuff in other regions bigger than the pivot, the 20, the 10, the 11. But again, those are positions where we can't be guaranteed that it will be bigger than the pivot. So it's the yellow regions which are guaranteed to be bigger and smaller than the pivot. And that gives us the guaranteed 30-70 split. Okay, so that proof was hard work, showing that this deterministic choose pivot subroutine guarantees a 30-70 split or better. And you probably feel a little exhausted and like we deserve a QED at this point. But we haven't earned it. We have not at all proved that this deterministic selection algorithm runs in linear time. Why doesn't a guaranteed 30-70 split guarantee us linear time automatically? Well, we had to work pretty hard to figure out this element guaranteeing this 30-70 split. In particular, we had to invoke another recursive call. So maybe this was a Pyrrhic victory. Maybe we had to work so hard to compute the pivot that it outweighs the benefit we get from this guaranteed 30-70 split. So we still have to prove that's not the case. Even in conjunction doing both of these things, we still have our linear time bound. We'll finish the analysis in the next video.